We have discussed in this course so far about how to discretize several types of differential equations, and those types include the diffusion type of equations, both steady and unsteady versions. And we have seen that based on the discretized equations, in many cases we could come up with a system of linear algebraic equations. So, the whole objective of the discretization method was in those cases to convert the governing differential equation into a system of linear algebraic equations. The objective is of this type because numerically it is much more convenient, or it is possible rather, to solve a system of linear algebraic equations rather than directly solving a differential equation, because standard methods of numerical solution of systems of linear algebraic equations, those are well known. So, now what we will do is we will try to look into the standard methods for solution of systems of linear algebraic equations, keeping in mind that we have our interest in applying these methods for solving the problems which are for solving the equations, linear algebraic equations which evolve due to discretization of the CFD problems that we have discussed so far, or we will be discussing subsequent to this consideration. Now, to begin with, we will begin with a level of high school or junior high school type, and we will just consider very simple equations to get first some insight on the nature of the equations and the nature of the solutions and so on. So, let us consider these following equations. Say equation number 1 or system of equation 1, x plus y is equal to 1, or let us make it 2, this is 1. Second problem, okay. Third problem, fourth problem, and a fifth problem. These are all very simple types of equations, and these equations people get familiar with these days in very junior high school classes. Now, our objective will be to look a bit deep into these equations and find out that what are the special characteristics of these equations, or how the characteristics of these equations differ from one another. Let us consider the first one. So, x plus y equal to 2, 2x plus 3y equal to 5. So, the standard method of solution, if you apply here, you are readily successful in doing that. For example, you can multiply the first equation, equation 1 by 2 and subtract that from equation 2, or equation 2, subtract equation 2 from that. So, if you do that, so 2x plus 2y equal to 4 and 2x plus 3y equal to 5. So, you have minus y is equal to minus 1, that means y equal to 1. This one you can now utilize in equation 1. So, equation 1 will give you x is equal to 2 minus y, that is 2 minus 1 is equal to 1. So, it can be the simplest possible type of equation, and there is hardly anything to discuss on this. It is straightforward in a sense. You have two equations, two unknowns, and what you are doing here is essentially an elimination, that is you are eliminating one of the variables in preference to the other and solving that particular variable first, and using that you are using the other variables, you are solving the other variables. Now, let us go to equation number the problem number 2. So, here you have x plus y equal to 2, 2x plus 2y equal to 4. So, if you see that if you readily give this problem to a junior high school student, there will appear to be some anomaly. Of course, at this level you know that there is no anomaly associated with it, but the apparent anomaly is there because of the fact that you see that there are two equations with two unknowns. So, this should give some solution. Yes, it is giving some solution, but not a unique solution. So, it is not possible for a school student to find out a unique solution to this system of equations, not just for a school student, for anybody it is not possible to find out a unique solution. The reason is that these are two equations, but not two independent equations. So, these equations are considered to be linearly dependent equations, because the second equation is just a constant multiplier of the first equation. It could also be that you can form a third equation which is a linear combination. So, some additive effect and some multiplying effect, for example, of the first two equations, just like as an example, if you multiply equation 1 with 2 and add that with equation 2, so you will get 2x plus 2y plus 2x plus 2y. So, 4x plus 4y is equal to 8. Again you have designed an equation which is elusively new, but it is not a new equation, because it is not a linearly independent form of an equation disregarding the existence of the previous two, a linearly dependent form of the previous two existing ones, and even the second one is a linearly dependent version of the first one. So, effectively no matter you can go on writing so many equations based on this, but effectively you have only one independent equation with two unknowns. So, here you have number of independent equations less than the number of unknowns, that is what you have to remember. We will formalize these statements subsequently, but we will keep in mind that if that is the case, it can be easily observed that you have only one independent equation and two unknowns. So, you can have infinitely large number of possible solutions. So, you can substitute any value of x, the corresponding y is 2 minus x. So, its solution is y is 2 minus x. So, you independently input whatever value of x you like and you will get a corresponding value of y. So, we should be aware of the fact that it is not a unique solution that you can expect if you have number of equations same as number of unknowns. it means absolutely nothing when we say that number of equations same as number of unknowns. Many times when we are mathematically modeling a problem, we express our satisfaction in seeing that we are having number of equations same as number of unknowns, but many times we do not check that those are independent equations or not. If those are linearly independent equations, then we can make such a statement. We will see that what are the conditions which further lead towards that, but if those are not linearly independent equations, then obviously that consideration cannot be applied. Then let us consider the third problem. So, x plus y equal to 2, 2x plus 2y equal to 5. So, here you can see that you have equation 1 and equation 2, they are not linearly dependent, that you can see, because if you multiply equation 1 by 2 you will not land up in getting equation 2, right. So, if you multiply equation 1 with 2, what you get? If you multiply equation 1 with 2, you get 2x plus 2y equal to 4. From equation 2 you get 2x plus 2y equal to 5. So, if you want to equate these two, you will end up with 4 equal to 5, right. So, obviously these do not have a solution. So, the situation is you have number of independent equations 2, number of unknowns 2, but you do not have any solution. If you make a sketch of these two equations in the xy plane, you will find that these two are two parallel straight lines. They have the same slope because the y by x coefficient is same for both. So, they are parallel straight lines, and since parallel straight lines do not intersect, you do not have their common solutions. So, these are typical cases that we encounter, but these cases are somewhat special in a way that these cases involve the right hand side which is not equal to 0, but you could also have equations where the right hand side is 0, which are called as homogeneous systems of linear algebraic equations. So, if you have the right hand side equal to 0, then such examples are given in these problems 4 and 5. So, we for discussion sake we can demarcate between the cases 1, 2, 3 and cases 4 and 5. So, for case 4, what we can see that here by observing the equations you can come up with a solution which is valid always, that is x equal to 0 and y equal to 0. So, x equal to 0 and y equal to 0 trivially satisfy these two equations, and that is why it is called as a trivial solution. So, you have trivial solution but are there non-trivial solutions? You do not have any non-trivial solution. Whereas, if you go to the example 5, you have again the issue of linear dependence coming into the picture. X plus y equal to 0, 2x plus 2y equal to 0 is a multiplier of equation 1 with 2. It is not a linearly independent version, it is just a dependent version of equation 1. As it is so, we can write this equation system solution as y equal to minus x. So, this also has a trivial solution, x equal to 0, y equal to 0, but beyond that it has infinite number of non trivial solutions. So whatever is the value of x, you can have the corresponding value of y as minus of that x. So infinitely large number of solutions will exist. That includes the trivial solution, but you also have non trivial solutions. Now these are certain observations that we can get from very simple systems of equations. The big challenge is that how can we extend these equations to a general case of a system of n number of equations with n number of unknowns. How can we extend or extrapolate these concepts? To do that, what we will consider is we will consider a matrix form of these equations. So let us again come back to the equations one after the other. So equation 1 has a matrix form 1 into x plus 1 into y, 2 into x plus 3 into y. So this one. You can clearly see that the distinction between cases 1, 2 and 3 that originated out of the difference in the coefficients. Not only that, also the differences in the right hand side, because in some cases the coefficients are equal like cases 2 and 3, but what mattered in the differences in the nature of solutions is that their right hand sides are different. So it is important to characterize the coefficients, also it is important to characterize the differences in the right hand side. So we can write a unified representation where we write the coefficient in one side and also we just make a partition and write the right hand side together with it. So this part where you have just the coefficient, which is this same as this one, this is called as the coefficient matrix. And the bigger picture which is there, that is called as augmented matrix, as if the coefficient matrix is augmented to include the right hand side. So for the case 1, let us identify what is the rank of the coefficient matrix and what is the rank of the augmented matrix. Why we are interested in the rank of the matrix is that the rank of the matrix essentially talks about also the sense of linear dependence and independence between different equations. So if you consider the rank of the coefficient matrix, let us recall that what is the rank of a matrix. If you have a matrix of rank R, that means there are two things that need to be satisfied. So let us note that rank of a matrix is R if it has at least one non-zero minor of order R, all minors of order greater than R vanish, that is become 0. What is a minor? Okay, we can go into a formal definition, but it is just a determinant that you can extract from the matrix in very simple terms. So, rank of the coefficient matrix, if we have to find out, we have to find out that what is that R, so that it has at least one non-zero minor, that is one determinant that you can extract out of it. It has at least one non-zero such determinant, and any minor of order greater than R vanish. So, to do that we will consider the highest possible order determinant that we can extract from it. So, what is the highest possible order determinant we can extract from it? Determinant of order 2. So, if we extract a determinant of order 2, then what we can see here, we can extract any 2 second order determinant, but just let us concentrate on this one, the one which is boxed with the red color. So, the determinant value of this is 3 into 1 minus 2 into 1. So, it is non-zero. So, it is good enough that you have got at least one non-zero minor of order 2, and any minor of order greater than 2 will vanish, of course, because it is not there. So, what is the rank of the coefficient matrix? 2. We are still on discussion with regard to the example 1. Rank of the augmented matrix, that also is 2, because you can extract say some 2 by 2 from the augmented matrix, say this one as an example, the green marked one. So, 5 into 1 minus 3 into 2, that is non-zero. So, the observation is rank of the coefficient matrix equal to rank of the augmented matrix equal to 2. This 2 is equal to our n, where we have considered that you have n number of equations with n number of unknowns. Let us do the same exercise for the example 2. So, let us write the coefficient and the augmented matrix. Coefficient matrix 1 1 2 2, then the augmented will include 2 and 4. So, this is the coefficient matrix. What is its rank? So, if you consider the determinant of order 2, that is 0, 2 into 1 minus 2 into 1, and therefore its rank is 1, because any one order determinant, that is individual terms that you can extract, of course this is non-zero. So, rank of coefficient matrix equal to 1. You can see that in a way it is talking about a linear independence, here it is a linear dependence. Rank of the augmented matrix, so of course in the augmented matrix you can extract this determinant, but you can also extract other determinants which are non-zero, right. For example, this one, but here that is also coming out to be 0. So, that shows that you can have the second equation as a perfect multiplier of the first equation, because you can see that when will the determinant be 0? You will have the determinant 0 when it may be possible that there are 2 rows and the rows are identical, right. So, here instead of the rows being identical, what you have? You have one particular row as the other row with a constant multiplier 2. So, if you extract the multiplier out of it, then what it becomes? Then what it becomes is that the two rows are the same. So, two identical rows means basically they are the same equations, just you have the constant multiplier as 2. So, what we get out of it? We get out of it is that the rank of the augmented matrix, that is also 1, because you cannot extract a second order non-zero determinant out of the augmented matrix. So, rank of the augmented matrix is 1. So, the observation is the rank of the coefficient matrix equal to rank of the augmented matrix equal to 1, which is less than n. Then let us consider the third example. In the third example, let us write the coefficient matrix and the augmented matrix. So, let us mark the coefficient matrix with the red box as we have done earlier. Here, what is the rank of the coefficient matrix? 1. The coefficient matrix has not changed from the previous example. So, the rank of the coefficient matrix still remains to be 1. What is the rank of the augmented matrix? Here the rank of the augmented matrix is 2, because of course you can extract a determinant with 0 determinant value like this one, but you can also extract a non-zero determinant of order 2, like the determinant of this is 5 into 1 minus 2 into 2, and that is non-zero. So, that means rank of the augmented matrix is 2. So, rank of the coefficient matrix is not equal to rank of the augmented matrix. These three cases may now be summed up. So, how can we sum up these three cases? For a system of non-homogeneous equations, which are examples 1 to 3, there are three possible cases. Rank of the coefficient matrix equal to rank of the augmented matrix equal to n. What is its consequence? If that is the case, then that will give you a unique solution. Then rank of the coefficient matrix equal to rank of the augmented matrix less than n. This will imply infinitely large number of solutions. And rank of coefficient matrix not same as rank of augmented matrix, which implies no solution. So, this is for non-homogeneous equations. Now, let us try to get the corresponding inferences for homogeneous equations. Now, when you consider homogeneous equations, you have to keep certain important things in mind. The first thing is that there is no requirement of putting any augmented matrix here, because right hand side is 0, right hand side will have no contribution. So, we can just infer on the nature of the solution based on the coefficient and determinant of the coefficient matrix. So, in example 4, the coefficient matrix is 1 1 2 3. What is its corresponding determinant? It is not equal to 0, whereas in case 5 the corresponding determinant 1 1 2 2, so determinant is equal to 0. So, what we can conclude, for a system of homogeneous equations, remember both homogeneous and non-homogeneous we are considering only linear algebraic equations, not non-linear. For a system of homogeneous equations, determinant not equal to 0 will imply only a trivial solution. And determinant equal to 0, this implies infinitely large number of solutions, non-trivial. So, what we have got at the end, these are certain rule bases that you have learned through your elementary courses in linear algebra, and this is a brief recapitulation of that. The whole objective of going through this very simple route or well understandable route of coming up with these kinds of inferences is that let us not consider these as certain rule bases which cannot be retrieved if you have forgotten it. So, you can see that through very simple examples you can retrieve very easily that what can be the nature of the solution given you have found out what is the rank of coefficient and augmented matrix for non-homogeneous equations and the determinant of the coefficient matrix for homogeneous equation. So, you need not forcefully remember these, you can see that very easily you can recover from simple examples of systems of algebraic equations with just 2 equations and 2 unknowns as a matter of example. Now, why we are going through this exercise? We are going through this exercise because we have say obtained some discretized equations. Now, the discretized equations have given rise to certain system of linear algebraic equations. We need to first assess that what is the nature of the solution. For example, if you have a system of non-homogeneous equations and then you are assessing the solution and you are getting that rank of coefficient matrix equal to rank of augmented matrix which is less than n, say this case you have obtained, that means it may not be a well posed boundary value problem. So, somehow if you had a differential equation you can always discretize it into a system of algebraic equations, but where is the guarantee that it is well posed? So, we have seen that one of the hallmarks of a well posed boundary value problem is that it will have a unique solution when you solve it. So that uniqueness of the solution will be disturbed if you could have infinitely large number of possible solutions, and that means you can suspect that perhaps there is something wrong with the definition of the problem itself rather than like your mechanical exercise of discretization. So the nature of solutions of a system of equation, assessment of that, to me it is a very critical thing before solving the equations itself, because that will give you a clue and an insight on what you can expect out of the solution of the equations. Now the next issue is that once you have solved or once you have obtained the nature of the equations and say you are satisfied with that, the next objective will be to solve the system of linear algebraic equations. So what could be the method of solutions? So now we will discuss on the solution techniques for systems of linear algebraic equations. For systems of linear algebraic equations. Broadly, the solution techniques are of three types. The first type is called the elimination method. Then iteration method, and third is gradient search method. We will cover some aspects of all these methods to whatever extent and to whatever details possible within the scope of this particular course, but we will start with the elimination method because that is the most intuitive one, and then we will talk about the iteration method. The gradient search method is based on an optimization technique, and we will see that how that optimization technique also leads to the solution of systems of algebraic equations, and our initial effort will be on the elimination method. So elimination method. From the name elimination, it is quite clear that what we are attempting to do in an elimination method. We are attempting to eliminate variables. So if there are two equations with two variables, we first try to eliminate one of the variables. Let us look into that example. So if you have x1 plus x2 is equal to 2 and 2x1 plus 3x2 equal to 5. So what we essentially try to do, we try to have equation 2 and subtract equation 1 into 2 from that. The objective is that when you multiply this by 2 and subtract, x1 will be eliminated. So effort is to eliminate so in this way, if there are three equations, let us take an example with three equations, x1 plus x2 plus x3 equal to 3, 2x1 plus 2x2 plus 3x3 equal to 7, 3x1 plus x2 plus 2x3 equal to 6. So, if you consider these equations, now you can eliminate x1 and x2 or x2 and x3 or any two of the 3 variables to solve the remaining one. That elimination may not be very systematic. So, usually when we take up these problems in junior high school classes, we try to do it in the most optimal manner in which we think. In that process we may not do it in a very systematic way. So, a systematic way means something which has a common algorithm that can be implemented with a computer, whereas when we do it in high school classes we do it with our intuition, which is many times more effective than what you could have done with a computer, but at the same time it is not as fast as what you could have done with a computer. So, to have a corresponding understanding, what we will do is we will now think that how we could systematically do it in an algorithm that can be easily translated to a computer program. So, to do that let us try to do it step by step. This is equation 1, this is equation 2, this is equation 3. So, if you now consider equation 2 minus 2 into equation 1, what it will give? So, 2x1 minus 2x1 that will be gone, then 2x2 minus 2x2 that will be gone, 6x3 minus x3. So, oh sorry 3x3 minus 2x3, right. So, x3 equal to 7 minus 6, that is 1. Then equation 3 minus 3 into equation 1, so that this 3x1 this term is eliminated. So, what you get? So, 3x1 then 3x1 gone, 3x then x2 minus 3x2 is minus 2x2, then 2x3 minus 3x3, so minus x3 is equal to 6 minus 9, that is minus 3. So, in this way what you have achieved is as follows: the coefficient matrix originally was 1 1 1, then 2 2 3 3 1 2. Let us also write the augmented matrix, because right hand side here is there non-zero. So, this is now transformed to 1 1 1, then 0 0 1 0 minus 2 minus 1, and the right hand side 3 1 minus 3. So, what has happened in this particular example is a very special case. I have very carefully chosen this example because if you now try to eliminate using the same policy as that you used in the first equation, you may be in a little bit of a trouble. Why? So, you are how you have eliminated the variable, the first variable here, you have eliminated the first variable by effectively equation 2 minus 2 into equation 1. So, we will see that equation 2 minus 2 into equation 1 when you say, then equation 1 has a coefficient which has a particular characteristic, it is bounded by some values, but you do not expect that to be 0. Now, if you do it for this particular equation, then for this particular equation if you try to eliminate, you see that if you now try to do, if you try to eliminate this variable using this equation, now whatever you multiplied with this is 0. So, it does not work. So, for example, if you want to eliminate x2 by considering equations 2 and 3, then I mean how do you do that? If you consider the elimination of this particular column, here you can see that what you have eliminated, you have eliminated all the terms in the first column below the diagonal term, and this particular row was acting like a pivot, using which, so you can see everywhere you have used equation 1 some multiplier of that one to eliminate something from equation 2 and 3. So, this is like a pivot, using the diagonal element of the pivot you have eliminated the corresponding terms in the column. The same thing if you want to do equation 3 minus this one, then you see that like minus 2 minus whatever into equation this one, that will remain as minus 2. So, what could be a way out? You could interchange the order of the equations. So, you could also reorder so we come up with an example where we see that reordering of the equations may be necessary. This is what we will keep in mind. So, how we will reorder? We will keep x1 plus x2 plus x3 equal to 3, 3x1 plus x2 plus 2x3 equal to 6, and 2x1 plus 2x2 plus 3x3 equal to 7. So, this is equation 1, this is equation 2, this is equation 3. So, then what will be your corresponding equations? 1 1 1 3, then the third equation now will become the second equation. So, 0 minus 2 minus 1 minus 3 and 0 0 1 1. So, in this way what you have achieved is something very special. You have converted the system into an upper triangular matrix, all terms below the diagonal are 0. So, now from here you can easily solve for x. So, x3 equal to 1, then what is x2 is minus 3 plus x3 by 3 minus x3 by 2, that is 1, and what is x1? 3 minus x2 minus x3, that is 1. So, again we could make this problem or break this problem into two parts. One part is forward elimination, convert coefficient matrix to upper triangular form. So, in that process you have eliminated many variables, so that finally you will get x3 equal to what? In general, for a system with n number of equations, xn equal to what? So, that is part 1, and part 2, once you have found out what is xn or x3 in this example, using x3 you have substituted that back into the second equation to get x2, and these two back in equation 1 to get what is x1. So, backward substitution. In this particular example, because of a particular simplicity, the forward elimination was over in one step, but usually you will not have the forward elimination over in one step. How many steps you will require for these three equations? So, what you expect is that in the first set of forward elimination, let us consider a different example where you require the full number of steps. Maybe let us change one of the coefficients, say let us make it let us try to see how many steps we can complete the elimination for this particular case, for these three equations. So, the first step of elimination is, so first let us write the coefficient matrix 1 1 1 2 1 3 3 4 2 equation 2 minus 2 into equation 1. So, you will have x2 minus 2x2 is minus x2, three x3 minus 2x3 is x3, 6 minus 6 is 0. Then E3 minus 3E1, 4x2 minus 3x2 is x2, 2x3 minus 3x3 is minus x3, is equal to 9 minus 9 equal to 0. What you see here? So, this is not an improved version of the problem. This is where I am trying to show you through repeated examples that the equation may look like to be elusive, I mean it may just be a change of coefficients, but you can see here that the elimination method will fail here also. It will fail not because it does not have a solution, but it has infinitely large number of solutions. So it shows that equation 2 and equation 3 are not linearly independent. In fact, if you multiply equation 3 with 2 by 3, you will get equation 2. Is it or no? Or maybe by some linear combination of these, if you, I think equation 1 plus equation 2 is equation 3, right, that is the linear combination, not 2 by 3, that is also not. Then what is the linear combination, you tell? No, 2/3 of E3 if you say, then what about these 4? So is there a mistake here? There is no mistake here. Then what is the linear combination, you find it out. So there must be some linear combination, because essentially, yes, 5E1 minus E2, right, 5 into 3 15 minus 6, so 5 minus 3 is 2, 5 minus 1 is 4, 5 minus 2 3, very good. So 5E1 minus E2 is E3, so there must be a linear combination, and because of this linear combination, see, it is not so easy to find out what is the linear combination if you do not, if you have not worked out yourself the linear combination, but somehow it will be revealed that it was a linear combination because of the fact that you come up with same equations. So the elimination approach will fail. So we have seen two examples where the elimination approach does not work straight away, it either goes through a twist where you require a reordering of the equations, or it will fail altogether. Now in the next lecture we will see that there are many more examples which are much more straightforward, and where you can directly use the elimination approach through the forward elimination and backward substitution and find out the solution of the systems of equations, and we will consider one particular systematic algorithm for that one, that is the Gaussian elimination method, that we will take up in the next lecture. Thank you.